Physicists believe in this thing called local gauge invariance. And in order for a theory to be local gauge invariant, we need to replace the covariant derivative by a gauge covariant derivative. This introduces a gauge vector field, mu, which itself induces interaction between fermionic field mediated by the vector field mu. And that's what we get in quantum electrodynamics. Mu has to be massless for the theory to be local gauge invariant, and it also has to transform this way. The problem is for weak interaction, the mediator of the interaction, which are the Z0 and the W plus minus, are heavy. They are gauge field but with a non-zero mass. Therefore, we are going to solve this problem by introducing a new mechanism, the Higgs mechanism, which is based on spontaneous symmetry breaking. So we have introduced spontaneous symmetry breaking, first in the case of global gauge spontaneous symmetry breaking. So we start with the Lagrangian, which is global gauge invariant. We don't care so far about local gauge invariant, so that's why we only use covariant derivatives. But the spontaneous symmetry breaking happens when the mass term is negative. That produces a degenerate vacuum with a non-zero value for the field. And by picking up one vacuum and expanding around this vacuum, we have two modes. One is climbing up the wall, which has a non-zero mass, and the other one is a Goldstone mode, which has a zero mass and which corresponds to rolling along the gutter. But so far we described spontaneous symmetry breaking using only global gauge transformation, and now we need to ask the question what happens in the case of a local gauge transformation, spontaneous symmetry breaking. And that is what gives rise to the Higgs mechanism, and will explain the non-zero masses for some gauge field like the Z0 or the W's.